and we will begin the third lecture given by Gregor Kasieczka. Okay, please go ahead.
Thank you very much. 1 second. There we are. Okay, can you hear me all right? Very good, thank you. So now we jump in a bit spontaneously into the second lecture, but I'm sure we can catch up in a moment. So first I would like to apologize. I had counted on a few more moments to clean up a few more slides towards the end of this presentation. So a few of the things might be a bit less polished than I would have liked them to be, but overall I think the content should not change very much under that. So the topic of the second, or the third topic actually, as we progress through the machine learning material that David and I had discussed together, is to go to our generative models. We do have a bit of an overhang from yesterday in the sense that there's one more topic on the type of classification problems that I would like to talk about, and that will very naturally lead us into something that's actually even a bit more broad than generative models, namely the question how we can use the loss function of the network to do interesting things in the training. So far we've focused on architecture, now we're also going to get to play with the loss function. So this is just a summary from yesterday. We've had an extensive discussion about the different architectures sketched in this overview, the machine learning landscape of top tagging. And I hope what you took away from yesterday was firstly maybe a few memories of the different specific architectures and the specific types of representation we can use for data. And secondly, this general spirit that we can encode physics information and we can encode properties of the data that we know about with our domain expertise into, for example, the architecture of the network to increase the performance and to make learning more easily. There is one very, very, very successful machine learning architecture that has only started to gain attention, especially in physics, after the landscape paper, and that I briefly wanted to introduce just so you've heard it, because I think this is a term that will come up again and again. These are called attention-based networks or transformer networks. And if you remember our discussion of LSTMs, so of recurrent networks, so of architectures for text or sequence processing yesterday, then we made the observation that the ordering of the sequence, of course, for a text, it's natural. You read words from left or you read symbols from left to right, but it has the big disadvantage that if you train a recurrent architecture that processes one letter or one word one after the other, either the first one or the last one has an outside influence, typically the final one. So you have a dependency on the ordering that may be not optimal because when you get to the end of the sentence, you forgot what it actually started with. And one problem where this actually is particularly important is a translation task. So think of having a text in some language, Korean, and you want to translate it to English or the other way around. So you want to map a sequence to another sequence. And the problem with this order dependence was that different languages have different sentence structures, different ways of ordering the words. So for example, the German language is very famous for very often burying the active verb at the very, very, very end of a long sentence, and people have forgotten what the sentence was about when you arrive at the end. So this is a problem if you have something that maps one-to-one, item by item, because it might already have forgotten what it should care about by the point it gets to that element in the translation. And this inspired the idea of including something called attention into a translation task. And attention very simply, well, it's not so simple, but as a basic concept, and this is what we should take away from this, attention for a sequence-to-sequence task, for example, first consists of a network that learns an encoding for all the elements in the input and all the elements in the target. and it builds a correspondence. So, and the correspondence, this looks a bit abstract now, but you can really think as you learn one vector out of the inputs, you learn one representation of each of the elements as the output. Both of these vectors have the same dimensionality, and the amount of agreement you can just calculate via the scalar product. So essentially, the scalar product of the two encodings tells you, for translating the first word, how relevant is each of the words in the input. This way, the network can figure out how much attention, obviously that's where the name comes from, pay to each of the elements. And this way, you can have a structure that is, in principle, a sequence-to-sequence task, but is not restricted to this bias of just paying attention to the first or the last word anymore, but it's more flexible in deciding which parts of the input are actually relevant. And as I said, I don't want to go too much into detail, but attention is being picked up very strongly in the computer science side. So it originated in this text translation task, and we'll look at one example in a moment to illustrate what I mean. But it's also, for example, being applied to show that a network can very easily learn this principle of convolutions is, you can see, as a subcase of attention, because a convolutional kernel tells the network it should pay attention to a local region in the input. So you could also imagine training an attention type network that in principle has access to all the pixels, but that learns that for making a prediction about one specific pixel, it needs to consider the local neighborhood primarily. So this is all learnable, and even though it started in language modeling, it's applicable more general. So here is just an example of a translation between English sentence and the French sentence, and how much attention you would pay for each, what's the attention coefficient between each pair of words. And I don't know how familiar you are with the French language, but the French have this interesting property that acronyms are inverted. So the European Economic Area, which is a common term, would be the Zone Économique Européenne. And you see that you have a relatively linear relation because the sentence order is more or less the same. But then you have this off-diagonal element that shows you, oh, the network figured out that these words need to be considered in a different order. So, okay, we're physicists. We don't care so much about translating European language legal texts. Let me just, as I said, I don't want to go too much into detail because we want to actually be moving somewhere else, but just to give you one last look at the top tagging problem and at a few advancements in this. So there have been a few attempts of actually applying attention to top tagging. There is this one by Zurich people that essentially directly applies the attention problem to the type of graph network we looked at yesterday. So you remember the graph network where we had the local neighborhood in the graph that the algorithm used as an input. The attention network can be used to more specifically focus on a subset of particles to use as the actual inputs. And this one by Hulin and collaborators, this is also what I'm showing here, called part T, is relatively complex. So I don't want to go into the architecture details here in this lecture. The key point is that they're using particles as an input, and they're also considering all particle pairs. They're called as interactions, but it's really just all doublets of particles as additional instances, and figure out how to process them most efficiently. So the architecture diagram is here. You see, it gets a bit messy. But the reason I wanted to point this out is because they also compare to the top tagging landscape data set. And I will first show the numbers and then try to give a bit of context, because this is quite an impressive change. So these are reproduced numbers primarily from the top tagging data set. So the landscape we've talked about before. And this last line is this new improvement here. So they show that they actually quite impressively do better than all the other methods. So we have here, for example, the rejection at a 30% efficiency, which is a nice metric because it gives big numbers that are easy to interpret, that is quite bigger. In the accuracy and the area under curve, of course, this turns into diminishing results. So this is doing much better. And I wanted to highlight this result for two reasons. First, it looks nice and it uses attention. Secondly, they've done something very interesting that is a concept that is applicable beyond the specific architecture and beyond the problem of attention learning. What they have done is called transfer learning. Transfer learning means to pre-train an algorithm on a different data set and then only to fine-tune it on the data set that you want to use in the end. So they had actually created a second chat data set they call chat class with 100 million examples. And if you remember, the top-taking landscape data set is 1 million examples. So this data set is 100 times as big. It's also slightly different composed. They use a different hadronization model. They have more features included. They have more particles included. So it's a bit of a wider data set. And what they can do is you can train this architecture on this larger data set, let it find the best performance there. And in general, as you maybe also have observed in the exercises, more data can lead to better performance. And once this is trained on this much larger data set, you can fine-tune, retune it to the actual problem that you care about. And this is what they've done here. So they've pre-trained on the chat class data set and then fine-tuned it on this top-taking landscape data set. As I said, you probably don't care so much about the absolute performance numbers, but this concept of transfer learning, I think, is very important to keep in mind, especially for problems where you don't have much training data available. So you could imagine that you have some region of phase space, some very rare process that is heavily suppressed, and you only have a handful of training events, but you still want to use a relatively general machine learning architecture. So you could imagine doing a pre-training on the larger data set and then see if just by fine-tuning it, by showing it a few examples of the data set that you actually care about and changing the weights for that, you can get a good performance. I think transfer learning is an interesting strategy that we are hardly using yet in the field successfully. In, let's say, outside of physics, this is much more common. For example, these large image classification networks that are produced by Google, for example. They are pre-trained on many classes of images. And if you want to write a phone app to do some classification problems, maybe you want to identify butterflies, as some of us are interested in, then you could very easily take that model and pre-train it to the specific types of images. And you just need to show it a relatively low number of the images of the classes that you care about to fine-tune it to that specific problem. So transfer learning is just an interesting tool to keep in mind. Sure?
Is the line above that, they train their
Oops.
on
I think that's how I understand it, yes.
So
Sure.
just with the top-taking data set, they got the same performance as the previous particle length.
Yes.
And
And then if you pre-train it on the larger data set, it does better.
cool. Oh, sorry, it looks like they also showed that transfer learning of particle length is not how this one is transfer learning.
Yes, so I think that the transformer really benefits the most strongly from the increased data set, which I think is also the general observation outside of this specific problem. Because, I mean, just conceptually, the transformer needs to learn more in the sense that it needs to learn more about the relations and it needs to figure out what is important. So I think it can be helped by more massive pre-training and it scales badly with low data. Okay, so we have we're now concluding the part about the specific top-tagging problem. I want to slowly move us towards other applications. And the first thing I want to mention is just that I have focused extensively on top-tagging because it's a popular playground and an important physics problem, but that is really not the only problem to be solved. And very roughly, if you can think of a particle, there's very likely somebody has developed some kind of tagging algorithm for it. And I think initially, let's say thinking back a few years, motivated by the different particles, by the different inputs, by the different symmetries that, for example, distinguish identifying hadronic jets versus finding long-lived particles via their secondary vertex and via their tracks. Initially, this has started as a bit of a disjointed effort because, for one thing, sequence-based models were explored. For other things, convolutional models were explored. But these recent architectures like graphs and transformers, they are flexible enough to handle all types of these data. So essentially, we're seeing a convergence of these different techniques that essentially any tagging problem that you might have, you can probably throw this massive thing at it and it will solve it nicely. I think there is, I don't want to say there's little innovation to be done because of course these things can be improved, but it's not that the specific nature of the particle that you're interested in or the specific nature of the data that you're interested in influences that much which architecture is chosen anymore, because we're now arriving at relatively general architectures that do very well. Here I just wanted to show an example that also early improvements in B-tagging. This is again a plot like we had for the landscape comparing a classical already machine learning based B-tagger versus deep learn based B-tagger. Again, gives a factor of 2 to 3 improvement in performance. So this is the general gain that we have from deep learning. Sure.
Is there any prospect for things being developed to push flavor tagging further in the sense of significantly improving that behavior or even have a strange part in this case?
How should I, let me answer this politically by saying that the people who develop.
Gregor, I'm sorry to interrupt you. Could you repeat the question?
Sorry, yes. So the question was if these type of tagging algorithms or tagging in general for flavor tagging are being considered to be improved, and if there's also something like strange tagging considered. So the short answer is yes, and the people who propose, for example, this party are also very active in CMS in developing these taggers. So essentially what we're heading towards is a multi-class tagger that you give a chat, and it gives you for each of the classes a probability saying this is light quark type, this is gluon chat, this is charm strange or B. So essentially you can imagine a multi-class tagger that takes both the colorimeter information, the tracking and the vertex information and combines this into one score per tagger. We already have this, but of course now these more complex architectures can be thrown at it.
So I can follow up. Maybe repeat the question. So I haven't seen anything public yet using strange tagging. So it's all internal, and that I want to for the future.
I think this is internal yet. I would need to look what the B-tagging group has put out. I'm sure it must have been shown at some point. Okay, I can dig that out for you and see what's the most public result on that. Okay, so to slowly bring us away, the next thing I would like to address is I have been focusing rather exclusively on addressing symmetry so far, but building it into the network architecture. Both because this is a relatively popular approach in physics, and secondly because, I mean, it's popular because it works. However, I would just like to briefly mention two alternative strategies that you could use or that you could even combine. The first one goes by the name of data augmentation. So if you know your data has some specific symmetry, so for example, we could consider images with a rotational symmetry, then we could either take out the symmetry by rotating all the images to be aligned along the z-axis in some way as was done for top tagging, or you could go completely the opposite way. Instead of encoding it in the network architecture and saying it should be invariant under the symmetry, you could for each example in the training data randomly add additional copies of it that are rotated by a random angle. This way, out of one training event, you get maybe 10 more for free. And if the training is limited by the available data, this is a very easy, in the sense that it's cheap and easy to implement strategy to make the training more efficient without needing to think about architecture and without needing to think about more complicated topics. So if there is an easy, simple symmetry operation that can be applied to the data, that it should be invariant under, then it can be used for, just to repeat the keyword again if you want to look for that, for data augmentation. The alternative is if there is a symmetry, we could also put the symmetry into the loss function. So for example, that, well, rotating it out is one way of putting it in the loss function, or just writing a loss function that is invariant under the symmetry. So again, it's a rotational symmetry, writing a loss function that does not consider the rotation solves this problem. Bit less explored for this specific task in physics, but the rest of the lecture will actually explore now different ways of doing interesting things with loss functions. The first example, before we go towards generative model, I wanted to talk about was briefly about stability, so how an algorithm can be made more robust. But before we go there, I can briefly pause for questions, even though we already have lively discussion, so maybe this is not needed. Okay, not needed indeed. Good. What do I mean with stability? So I'm sorry for this very beautiful drawing. I really need to replace this at some point. But if we're thinking about taggers, the mental picture that we have, or that I usually have, is that we have one observable at least, and we're looking for a signal that is peaked in that observable. And we have a background distribution that has some smooth shape. So in this case, we consider in blue a background distribution that is smoothly falling, and in red a small signal peak over that background. This AU just stands for arbitrary unit, so we don't need to worry about the normalization. And we pick the mask for some signal as the observable to look at. Now we want to apply machine learning. We use the best tagger from the landscape paper, or we use the part T, or any tagger that you've developed. And the hope would be that a supervised classifier trained for this problem will enhance the signal relative to the background. Enhancing the signal relative to the background will typically result in a distribution like this. So we observe that the relative fraction, the volume under the curve for the signal versus the volume under the same region for the background, has improved dramatically. So this is maybe a signal to background ratio, background to signal of 2 to 1. Here it was 5 to 1 or 10 to 1. So we definitely increased the amount of signal we have. But we've paid a price for this because, for example, if we train a top tagger, it can learn that the particle has a specific resonance mass. Well, it's at a specific value. So it will also shape the distribution of the background. We shape the distribution of the background. Here you see the background was smoothly falling before. After application of a random classifier, the distribution of the background is similarly peaked at the mass of the signal. Why is this bad? Well, I've explained in the very beginning of the first lecture the way an analysis typically works. And usually these taggers that we develop are only one element in a longer tool chain of things that stand between the data and the final physics observation. And the next step is usually to estimate the background distributions. And if you do the background estimation by fitting a function through the sideband and trying to extrapolate it in the signal region, you can very nicely do it in such a situation because you fit a straight line through it and you can predict the amount of background. But if the machine learning algorithm shapes the background in a funny way, you're out of luck. So background estimation becomes much more difficult. Which means that while you have, at first you think you have gained because you now have a better classifier, in the end you've made your life more difficult. So this is not where we want to be. And the answer to this would be to find some way to keep the background distribution intact while still enhancing the signal. And this is the slightly lengthy, but I think for a lecture this is useful, explanation what we mean with building a decorrelated classifier. So we try to build something that still enhances signal peak while leaving a chosen other distribution unchanged by this tagging. Of course, this will come at the price, and the price will be a decrease in the performance for the actual tagging task typically, but very often this price is worth to pay because it allows the rest of the analysis or the rest of the data processing to be continued. So how can we do decorrelation? And I'm going to, in a bit more detail, talk about two approaches, but first let me bring two things out of the way because they're also important observations on how machine learning works. The first one is what I call here obscurity. You could say, you could call it also the ostrich strategy. You could say, okay, I train my classifier, and all I do is I do not pass the mass as an input observable to the machine learning training. and because it does not have access to the mass, it should not learn anything about it, right? Well, the problem is, or the problem under quotation marks, is that the machine learning tools we're working with are essentially machines to find hidden correlations in the input observables. And if you have a list of inputs, for example, if you have the momentum of a jet and some n sub jettiness variables, the machine learning algorithm can still internally reconstruct the mass. So very often, just because you pass the mass as an input does not mean it will not learn a correlation with it. You can get lucky, but you're not guaranteed to. So we can't rely on that. A second strategy that works quite reliable is, before training a classifier, is to reweight the input distributions to be flat. So essentially, we assign a weight to all of these examples so that the signal and the background have the same shape. It's possible, it improves actually, it reduces actually the correlation, but it's, again, not entirely reliable, and it has some limited power, but it's definitely the first thing to try if you're facing this problem concretely. The first example I actually want to talk about is termed adversarial decorrelation. And this, I can't emphasize that enough. So if you don't understand this, ask until you do. Let me put it this way. This is a big conceptual step because we're moving the first time away from having one loss function that tries to solve for a specific problem to combining loss functions and to combining networks to solve for tasks. In this case, our loss function consists of two terms, a classification term that looks like the binary cross entropy that David introduced 2 days ago, and the second loss function for the adversary. So let's look at the architecture diagram and try to figure out what's going on. We have here our inputs, and we have two networks. So we're really using more than one network now to solve for task. The first network is the classifier. It really has the task of solving the classification problem. So you can think of the first network as being a network that tries to distinguish top quarks from QCD jets. So we know what the classifier does. This is what you've exercised. This is what we've discussed in the previous lecture. But now we add a second network, and the second network gets the output of the classifier as an input, and it tries to learn the invariant mass. So you can think of the loss function of the adversary either as a cross entropy or as an MSE-based regression that, from the classification score, tries to learn the mass of the jet. This sounds crazy. Why does this help? Let's think it through. So if any information about the mass is in the classification score, then the adversary can learn about it. So for example, if it's biased, if we know that the classification score is always too high for a specific mass, then the adversary can say, oh, if the classification score has a value that is a bit higher, so for example, if the classification score of 0.7 is the minimum value that we have for a higher mass, then the adversary can say, okay, if the classification score is 0.7 or more, then I'm pretty sure that, that this was a signal type jet. So it can learn about this, and we add this with a minus sign in the loss function. Therefore, in a sense, we punish the classification score if it allows the adversary to learn about this. This factor lambda is just a scaling parameter, so you can tune the relative importance of these two contributions. So again, with an adversary that can infer the mass, we can punish the classifier for learning something that we don't want it to learn. And there's a small problem from doing both of these things with neural networks, but in principle, for an arbitrary problem you have, you can combine networks with different roles as long as you can write everything in a loss function in a meaningful way. This is a priori possible. The one problem is multiple networks training simultaneously might be unstable and might be a bit tricky to set up. So for this specific problem, there are also solutions that get away without it. But conceptually, there's nothing stopping you from chaining together different networks that achieve different tasks and that make sure that your solution does what you want it to do. Yes?
So is lambda positive then?
Lambda is a positive constant, yeah.
And then the L classification, we heard about MSE and cross entropy and a few candidates.
Yes?
So what are the possible expressions for the L adversary?
You can either use an MSE for, naively you would use an MSE for the L adversary. So essentially trying to predict the mass is obviously a regression task, so you can put the MSE in there. In this paper, they actually show that their performance gets a bit better if they don't use the MSE, but if they use the mass spectrum and treat each bin of the mass as a separate category and throw a multi-class classification at this.
So that means you are using the mass information explicitly in the loss function.
You use it in the loss function, but not as an input, of course. Yes.
Or not as an input, but you do include the mass information in the loss, right?
Absolutely.
Yeah, but that means you are actually using the mass information explicitly in this entire training session, right?
Absolutely. You need to, well, you're giving it the mass so it knows that it can't learn about it. But you need to give it the mass for that. Absolutely. So you're making explicit use of the mass for this decorrelation. Definitely. But again, the important point is well, that's not even true. In principle, you could even consider giving the mass as an input to the classifier. It would not hurt the principle, because as long as you make sure with this adversarial training, it gets decorrelated away, you're safe. In practice, it turns out decorrelating against the mass is easier when you don't give it as an input, but this is again more of an empirical practical argument and not a fundamental one. Okay, so we have adversarial training. Very briefly, first because this is a nice additional application of loss functions. Second, because there's a paper that we worked on with David. Let me talk about an alternative way of...
Before go to the next slide, this slide, can you go back to the previous one? Yes. So here the example is a G prime from the QCD, and you reduced the impact from the gen mass, right?
Yes.
Then what would be the most important factor distinguishing G prime from the QCD now?
Sorry?
Then what would be the most important factor distinguishing G prime from QCD if you remove the gen mass impact? The feature for the distinguishing G prime from QCD.
Ah, okay. Okay, if you're interested about the actual physics application and why this is not a stupid problem to solve, let me maybe give you a bit more context. So the idea is to indeed distinguish, or the proof of concept here was to distinguish C prime from QCD for a new physics search. And one of the things that we never get from theorists is a specific prediction which mass of the C prime we need to look for. If you were to tell us the C prime has a mass of 1.7 TeV, you don't need to look at any other value, we would not need to do this. But for an experimental application, it can be useful to say, we want to have something that tags a resonance independent of its mass, because then you can use it for a resonance search for different values of the mass. You can also do other things for that. And I'll talk about parametrized networks a bit later, but this was the underlying idea. And so your question was, which features can you actually use as an input if you don't want to touch the invariant mass? So the main feature, now I don't remember if this was a subchat search or if this was a die-chat search, but if it's a subchat search, then the feature could be something like the n-subchattiness, because the C prime has a two-prong nature, whereas the QCD chats do not have much a two-prong nature. If it's a die-chat search, then you can look at something like an angular distance between pairs of chats, which fulfills the same role. Yeah, actually, the one thing that I said en passant, maybe I should emphasize a bit more. Especially for this problem, there are also alternative ways like parametrized networks that we'll talk about later. But for showing how decorrelation works, I think this is a nice toy case. Okay, so what's the one downside is that essentially this adversarial training is pretty unstable. So if you try it in practice, you will see it does not converge very well, because you need to convince two networks to arrive at the settle point of the loss function. It can run away in either direction. So there is one project that we did with David, and since the mathematics is a bit more involved and not so central to the argument, I will be very brief here and just try to sketch the basic idea, is that in some cases, and decorrelation is one of them, it can also be possible to, instead of adding a second network to fulfill a specific task, you can just write down a differentiable function to solve the problem. And in the case of decorrelation, there turns out there's one differentiable way of calculating a nonlinear amount of correlation. This is termed distance correlation. As I said, I don't want to go into the definition of the distance correlation, but the key point is that, again, we can just simply take the loss function, have the loss function of the classifier, and add an additional decorrelation term to it. And this way, it becomes more tractable to training and less unstable because you only have one network of which the parameters need to be optimized. So in practice, this is, I think, probably the most beautiful illustration we have of showing how decorrelation works, because it goes back to the distribution I've drawn before. So we look here, not at C prime tagging, but at the recast of an ATLAS study on identifying hadronically decaying W jets. And again, we want to decorrelate against the mass. So if we draw the mass on the horizontal axis and the fraction of jets passing the selection on the vertical axis, then we have the blue distribution before applying any cut. And this is a relatively smooth spectrum for the background. If we apply a cut on the classifier, just training it naively without any decorrelation technique, it adds this bump in the distribution, which is exactly the behavior that we showed that we don't want. Adding then a distance correlation term, or similarly an adversarial decorrelation term, the performance is pretty similar. The distribution after the cut exactly, or with very small differences, looks again like the distribution before the cut. So we can solve additional problems either by adding more terms to the loss function. Well, we can solve problems by adding more terms to the loss function, either a second network, or, and usually that leads to simpler training, differentiable terms that specifically address it. We can even go one step further. You've heard about the ABCD method, I think, prompted by Ben's presentation on Monday morning. The ABCD method is a technique for background estimation. So it assumes that you have a background distribution that in the features f and g is independent, meaning that the probability distribution factorizes. And with this, you can relatively easily show that the ratios of event counts in regions that are arranged in the grid like that, A, B, C, D, are equal. So the ratio of events in A to B should be equal to C to D, or any other permutations of this. And this is a very popular, by experimentalists, technique to estimate the background for a search, because if a signal, in this case shown by this orange distribution, is in the region A, you can imagine predicting the background in region A by taking the ratios in C, D, and B and estimating it. So in this case, the prediction for A would be the count in B times the count in C divided by the count in D. Okay, we have the ABCD method, and the ABCD method requires as an input two uncorrelated observables. The problem is, if I train a machine learning classifier, or if I just pick two physics observables, they will not be decorrelated. But again, we can just throw everything into one combined loss function. Say we want the loss function that gives us two functions, f and g, where we have one classifier type loss function for f finding the signal, one classifier type loss function for g finding the signal, and the distance correlation term that removes the correlation between f and g. So just to repeat this again, we can structure arbitrarily complex problems by just thinking a bit and putting the correct terms in the loss function together and then jointly training this whole procedure. This is still in the realm of classifiers, but this is already moving us towards the next topic that I want to talk about. So let me maybe pause here a quick moment for questions, and then we jump into generative modeling. Okay, no questions. I know this was a bit fast, and I know that this was a slightly advanced topic. So we're now making a transition. You're not allowed to ask questions. You're a co-author of all of this.
Have you looked more into like, so one thing you didn't mention is the decorrelation stuff is actually called used in the real world ML for, they call it AI fairness, or algorithmic bias. So when they want to train a classifier or something and make sure that it's not racist or sexist or something, they'll use these techniques.
Yes.
And to like decorrelate against those they call them protected features.
Yes.
And so I think we discussed in the past, you and I, like they invented the adversarial thing in the ML world too. Do you know if, have you looked further into whether they were first or like we were first, or they talk to each other? Do you know anything more about that?
So the short answer is no. And I think the biggest divide that I've seen so far, and that's why when I stopped looking into this further, is that in physics, the protected qualities we care about are typically real numbers, floating point numbers. Whereas very often in, let's say, societal problems, the protected variable is treated as either as a Boolean or at most as a 2 or 3 class difference. So these techniques don't immediately jump to categorical variables that easily, and I think that's necessary on the outside of physics data side, because of course the training sample for a hiring algorithm, it's not so easy to very quickly get 1 million identical examples of a hiring process, whereas we have it much easier there. So I think some of the types of problems that we solve are too technical for them, and on the other hand, if you talk about fairness of a hiring process, then the definition becomes much more subtle, because it's, what is it, equity, equality, blah, blah, blah. So I think maybe there is some exchange, but I'm not aware of anything, at least specifically with the hep approaches. Okay, thanks, David. So again, let me just repeat it once more. We're now making a big step away from classifiers towards generative modeling. And if you felt a bit disconnected by the last bits of the classifier because they were maybe a bit too advanced in the beginning of the school, this is now an entirely new topic, so you can start being confused from fresh. Or hopefully not be confused, which should be the desired state. So what we mean with generative models, very broadly, what we talk about is a situation where we have many images, and generative models are often shown and explained with images, but all of what I'm saying also applied to collision events represented as lists of 4 vectors, or to readout data of a detector, or maybe to some phase space points denoting some element of your theory. This is all fine, but for simplicity, I'll mostly be talking about images when we introduce the concept. So we have a database of many images, and what do we want? We want more images. And to a human, this is a relatively easy statement. But we need to be a bit careful, because we want more examples that are similar to the ones that are in the image set that we start with, but not identical. So for example, if I go to you and if I give you 10 pictures of a cat, or 10 pictures of different cats, and I ask you, can I please have more of this? Then I think you will take your camera and take the next picture of a cat you find in Seoul. You will not get the idea that you go to a copy machine, take one of the pictures I gave to you, make a copy and give it back to me. We all agree that this would be stupid. Or hopefully we all agree that this would be stupid. A machine learning algorithm a priori doesn't think it's stupid. We say we want more pictures of a specific kind, so we need to specify what exactly we mean with that, and we need to make sure that we avoid producing identical copies. So we'll be talking about a few methods to arrive at this. I will be introducing 2 concepts, and David will introduce the most recent one. Why do we care about this? I think the 2 main applications are both of very intimidating names, so let's unpack that. The first application that we can think about is what we call here fast approximative simulation, meaning, especially in particle physics, we've talked a lot about the quality of our simulation chain. We have high quality theory-based simulations that tell us how the hard process works. We have trained from data simulations of the hadron of parton shower and hadronization, and of course we have simulations that describe the material interactions in these very large detectors. This is great, but it's very compute intensive, and I have a specific slide on this a bit later in the lecture. So speeding this up by training a generative model that just can very quickly churn out more examples is a good strategy. The same could be considered for theory simulation. The second aspect is that we need to remember that the machine learning algorithm, all these neural networks that we train, in the end are differentiable functions, which means that if we train for a specific physics simulation problem, if we train a machine learning model that's approximated, we can sample from it, which is great, but we can also treat it as a differentiable function of its input. So it could be used for something like inverting the function and trying to learn, going from the data to learn about the model parameters. So there's this whole branch of likelihood-free inference and learning model parameters that uses surrogate models in a different way. I'm focusing on the approximative simulation, but just as an outlook, once you have a fully differentiable model that describes your physics and that describes your detector, the potential use cases are much larger than the specific simulation tasks that I'm going to talk about today. But let's start with a few examples, because the nice thing about generative modeling is that it's very easy to produce pretty pictures. So one very popular example is this person does not exist.com. So whenever you go to this web page, you get a new randomly generated face that by now looks fairly realistic. So there's a few artifacts, like his ear is funny, but in general, on the first glance, these look pretty good. And if you're interested in this kind of stuff, there's a million other versions of this X does not exist with many other generative models where you can see different outputs. So I'll talk a bit about more of the upsides and downsides of this type of thing, but this looks already pretty nice. Second example that is in the realm of generative models is style transfer. So we talked a lot about architecture yesterday. So I took a picture of the Hamburg concert hall, the Elbphilharmonie, tried to combine it with some supposedly Korean, I hope I'm not offending anybody, type of painting that I found on Wikipedia, and I tried to have the Elbphilharmonie rendered in the style of this Korean painting. I don't think it did a very good job of that, so I'm not going to hang that on my wall, but just to demonstrate other types of things. And something very recent is called Crayon, which is impressive because it combines a text-based model input with the generative modeling. So if you have not played with that, you should go there, maybe not during the lecture, because then you'll be too disappointed to listen to me, but you can do it in the coffee break, to crayon.com. It gives you a prompt where you can type in anything that comes to your mind and have a generative model try to predict what it should be. And well, you can see where my mind was at this week. So if we ask this generative model to predict pictures of Korean food, I'm not entirely sure if I recognize all the dishes, but it does a fairly credible job of how these things should look. Well, this looks a bit superimposed, but in principle it has understood the type of pictures it should reproduce. It gets interesting when we do something different and just put in some terms that probably don't have much illustrations. But you can see that a large enough model actually understands also tasks that it's probably not trying to do. So the interpolation and the extrapolation capacities of these models are actually quite impressive. I have a whole library of stupid things like that I've done on my computer, but I'm not going to bore you with the picture show of these. Good. So now that we're motivated about the exciting potential of generative models, both for physics and for art and maybe advertisement, let's see how they actually work. And let's start with the still in the realm of art illustration of the so-called Generative Adversarial Network, or GAN. I'm only going to use the word GAN. So I've drawn here a slightly extended diagram of the architecture. Let's look at the individual components. We have two neural networks again, one generator, in this case it's Picasso, and one discriminator. And very similar to the adversarial training for decorrelation, in the generative adversarial network, we're training these two networks against each other. We'll write down the loss function in a few moments. Let's just first try to understand what we're trying to do. So we have two networks that work against each other. The input to the generator is some random noise. And the output of the generator should be beautiful paintings. This might be a moment where you pause for a second. Why do we need noise as an input for the generator? Well, very simply, we've learned that the machine learning model is a fully defined deterministic function of a given input. If you have a fully determined deterministic function of inputs, how can you make it produce different examples? So for example, if I go to this web page, this person does not exist.com, each time I go there, it gives me a different face. If it's a deterministic function, it needs to have some source of randomness, some source of entropy to turn these random numbers into different outputs. But because if it would not have any input, then it would just return the same face again and again. Just as we said, if we go to the copy machine with the pictures of the cats, this is not what we want. So we need some random noise. In the end, this is a number of Gaussian distributions as an input. And the generator network has the task of transforming this random noise into beautiful pictures. So in the end, we want a function that learns to turn random noise, to transform this into meaningful paintings. And how do we achieve that? Well, this is exactly the point where the structure that we saw in the adversarial training for decorrelation comes in. So we have a second network that has access to a library of previous beautiful paintings. And it compares them. And the discriminator gives feedback to the generator just by writing down this joint loss function in such a way that we're slowly pushing the generator to try to produce better and better fake images. As I said, we'll be looking at the mathematics in a moment. First, try to understand this really as two actors competing with each other. So in the initial stage, the generator, the weights are just randomly initialized. So the fake image that the generator produces is poor rubbish. The discriminator gives some feedback, and slowly the generator learns to produce better images. And the training of this is usually done alternatingly. So we train the discriminator, meaning we do backpropagation and calculate the loss function while the discriminator is frozen. Then we train the discriminator while the generator is frozen. And this is repeated. So we have a better fake image. Okay, it looks a bit better. We're getting better fake images, and at some point, the images that are produced by the generator are actually, well, not entirely assembling the training data set, but that's not what we want. But we're arriving in the same category of beautiful paintings. So how does this look a bit more seriously? We have two neural networks. We already said that. And this is the same structure that we drew before, just arranged a bit differently. So we start with random noise, and again, the generator, the Picasso, has to take this random noise and turn it into an image. And we have access to a library of training images, beautiful paintings, of jets simulated by the detector, of anything that you'd care to simulate, and both of them are input into the discriminator, and the discriminator has the job of assigning a score, whether this image is either real, so whether it's from the training set, or whether it's fake, meaning whether it's from the generator. The loss function for this, it's a bit long, but it still fits on the slide. The loss function of this has two components. Oh, well, no, it's actually one component. And we can understand this now. So let's see. We have an expectation value of the log of d plus an expectation value of the log of 1 minus d. Does somebody recognize that? Guesses? What is this? This is a binary cross entropy. This is just a binary cross entropy for the discriminator. Here we sample data. Here we sample x from the probability distribution of data examples. So this is essentially sampling over the training set, and we have log D. So we want these to have a high score in the classifier. Here, we're sampling over C, and C is just some distribution of random numbers. So C is essentially what describes the random noise. And it's log of 1 minus D of G of X. So the discriminator applied to the generator output applied to the random number. But in the end, this is really just the cross entropy for a classification problem that we've encountered in the first lecture. You don't immediately recognize it because there's lots of fluff around it to write it the way we need it for this problem. But this is really just a binary classification entropy for this discriminator. And the only place that the generator shows up is here in the second term. So in the fact that we want that the discriminator tries to push the generator in, tries to identify images generated by this generator. This is all we need. And we can train this, as we said, jointly and iteratively. And it produces good images. And I don't have beautiful examples now because we started with the examples. OK. Big moment. We've introduced generative adversarial networks. Maybe we open the floor for questions, because this is really a point where if you're confused, it's a very good moment to articulate your confusion and hope that we can clean it up.
If different random noises makes different fake images, is it mean that really random?
Sorry, I'm not sure if I...
If random noises are different random noises, for example, different seed makes a different random noise. So if generator makes a different fake image from the different random noise.
Exactly. Each time, so, OK, a very good point. I've only talked about the training phase so far. Once you're done training, you usually throw away the discriminator, and you only care about the generator. And then whenever you want to produce a new image, you sample a new set of variables from your random noise. So you throw the dice, and it will assign to each value of the random noise, and it will assign a new output. So it really maps each output of the random noise to different images. That's how you get this variety.
Is it mean that really random? Because
well, OK. So first, of course, whenever I say random noise, I mean pseudo-random number generator. We don't care about quantum noise or any physical source of noise. This is perfectly fine. We're not doing cryptography. The second part of the question is a bit more tricky. And this is really addressing, actually, it's a natural transition to the next slide, so I'll go there in a moment. This is really addressing the function, what does the generator do? Because you could imagine that your training fails. And the generator does not learn to produce all space of possible images. This is a very, very core problem when training generative models called mode collapse. So we have an illustration of mode collapse here on the right-hand side. This is a result of a generative model that was trained to output numbers from the MNIST dataset. So you see the digits between 0 and 9. And in this case, it mode collapsed, and it only learned to produce the numbers 8 and 1. In that sense, you can start with random noise, but if you have a function that maps all the random noise always to the same value, of course, the output is not random anymore. So you want it to restrict itself to the manifold of beautiful images. So it shouldn't leave that, but it should cover that manifold of beautiful images well. So this is exactly the tension that the generative model needs to learn.
Thank you very much.
Thank you.
May I add some question? Oh, can you hear me?
It's from Zoom.
Oh, yeah, here. Yeah.
I was looking in the room.
Okay. So is there any some reasonable criteria for stopping this GAN learning? That because when the generator want to generate some perfect fake image, but however the discriminator want to classify the real and fake data. So when in the in human knowledge, we want to stop the learning whenever it's like a good model. So also my question is, when is the stopping point to
Oh, this
make
is,
this?
I'm very happy because you're all paying very good attention and you're asking exactly the questions I want to talk about next. So we can, I'm very happy with this. Let's see. Wait, but zoomed, no, there we are. So this is the next problem. A big downside of this simple generative adversarial network is that the loss function is very difficult to interpret. So the loss function can either be small if the generator is doing very, very well, or if the discriminator is doing very purely. So the loss function is not a reliable thing that tells you if the images are good. And finding a stopping criterion for training is actually quite difficult. So for physics problem, I'll talk about the physics example later. I think I still have half an hour left or so, which should be perfect with the timing. So I'll come to the physics example. But in the physics example, we can use as a stopping criterion some physical observables saying we want to simulate a specific distribution. We stop when the histogram in this distribution looks good enough. So this can be done. For image type classification, this is a bit harder. So you really need a human expert. There's research ongoing into how to actually assign a quality score to the output of a generative model. But as you say, this is not entirely trivial. Other generative models we're going to talk about today and tomorrow, or today and later today, have less of this problem.
Thank you very much.
Okay, thank you. Okay, I don't see other immediate questions, and we're already on the page I wanted to continue on anyway. So the problem we talked about is the mode collapse and the difficulty of interpreting the value of the loss function, similar to the issues we already had with adversarial training. And maybe as a very brief aside, I presented adversarial training for decorrelation first, but generative adversarial networks are slightly older. So I think the evolution went in the opposite direction. Just so I don't give you a wrong impression here how this historically came about. For the use of course, this doesn't matter. Let's look at the other two problems. Again, stability and convergence of learning. Because we have two competing networks that have slightly mismatched objectives, it can very easily go into a state where, for example, the discriminator is much better than the generator. So the discriminator immediately, no matter what the generator does, figures out that the images are fake and does not provide any useful gradients in the local direction, but always figures this out. Or in the opposite way, if the generator is much more powerful than the discriminator never has a chance to again provide useful feedback. So with this generative adversarial network setup, it's important to have some agreement between the capacity of these networks to avoid, for example, this vanishing gradient happens just if no matter what the generator outputs, the discriminator is always sure that it's a fake image. So we're essentially in the term and in the plateau of the classifier output, and there the gradients become very small. So these are technical things that with a bit of tuning can be overcome. We'll be introducing in a few moments one alternative version to a GAN that actually does a bit better with these. But in principle, this is a standard issue with training generative adversarial networks. One slight twist that is very important for physics applications are so-called conditions. So I'm sorry the loss functions are just getting longer and longer, but what do we mean with that? I showed you in the very beginning this person does not exist generative model. It's nice because it produces faces of people, but it has one big problem. It does not give you any control over the output you're getting. if you're thinking about the physics application, in most cases, this will not satisfy you, because I'm interested in simulating showers in calorimeters. If I want to simulate a shower in a calorimeter, I need to be able to determine the energy of the particle that produces the shower. I need to be able to define the particle type that initiates the shower. I need to be able to define the direction that I want the shower to start in, and so on. So for being practically useful for many physics applications, you want to be able to tell the generative model a bit more precisely what you want. And one very good answer to these is so-called label conditioning. You can imagine this the following way, that you add an input variable to the network that in the training and in the in the using phase tells it which type of image you want. So this could either be so this is the role of this variable y here. So we replace log of d of x, which was the discriminator term, and log of 1 minus d of g of c, which is the random number. We replace d of x with d of x conditioned on y, and we replace d of g of z with the condition on the label. So essentially this means that we have a family of networks that are sharing the weights, but that receive the type of image that they should generate as an additional input. And just by adding this, you can have conditioning on the energy or on the particle type. And it also has the advantage, if we think back of the problem that we've just seen here, this mode collapse. If we explicitly tell the generative model it needs to learn to generate the classes 1, 2, 3, 4, 5, 6, 7, 8, 9, and the number 0, then it cannot collapse into such a mode where it does not learn a specific class, because there are explicit terms in the loss function that ensure that each of them can be produced. This is one, let's say. The big advantage is that this allows to produce output in a more targeted way. The big disadvantage is that it requires you to know more about your data. Because in a simple generative model, a generative model is unsupervised. You have a pile of images, you throw the pile of images into the generative model, and it learns to produce more images. For a conditional generative adversarial network, you need to sort your images into the different piles corresponding to the different classes that it cares about, and you train, in a sense, each of them separately. Now, you could ask, why go through the trouble if I sort the images into different classes and train each of them separately? Why don't I just do 10 different generative models? So I could also say, for this problem of MNIST, I train one generative models only on the instances of zeros. I train one generative model only on the instances of 1, and so on. So a generative model for each of the classes. This is valid, right? If I already have to separate my images into the different classes, this is also perfectly fine to train separate models. The advantage of this conditioning approach is just economy with the weights, because there are some similarities between the different classes, and if we have one network that sees all the images in training at the same time, it's more easy for it to learn. So essentially, by this sharing of the different tasks, it becomes easier to train. Secondly, for disjoint classes, this is less important, but for the physics application, the big other advantage is that, for example, if we condition on energy, we can condition on discrete values, but we can see that the network actually learns to interpolate between different values. If you were just training one generative model for 10 GeV showers and one generative model for 20 GeV showers, it would be very hard to produce 15 GeV showers. But if you have a model that takes this as an input, you can also let it interpolate values that it actually did not explicitly see in the training phase. Or in general, if you have a continuous variable, then this is the better answer anyways. So we have to get mathematical for a brief moment. and this is one slide. You see there's a bit blank here, so there's one or two more things I wanted to add, so we need to do that verbally now. Let me introduce the word divergence. And this is one of these words where we need to be careful because they mean a different thing to a physics audience than to a computer science audience, apparently. So I only encountered the word divergences in this context when I started machine learning. Divergence is a general class of distance measures between functions or between probabilities. And the very popular of these divergences is the so-called Callback-Libeller divergence, DKL. The Callback-Libeller divergence is for two probability distributions P and Q, defined as minus the sum over examples of the probability of the event Pi times the logarithm of the ratio of the probabilities Qi and Pi. Okay. Why is this important? So we'll in a moment see that we can relate the training of the generative adversarial network to this Callback-Libeller divergence in a very nice way. So this will be important. But the Callback-Libeller divergence also plays a role in the training of the classifiers that we've seen before. You can think of this the following way. The logarithm of Q over I, what is the logarithm of a ratio of numbers? The logarithm of the ratio of numbers is the difference of the logarithms. So what we have here is Pi log Qi minus Pi log Pi. Okay. Pi log Qi is just a cross entropy that we introduced as the training term for the classifier. Pi log Pi is called the entropy of a variable. So the entropy is a measure of the information content of a specific probability distribution. So what this tells us is that the Callback-Libeller divergence between two probability distributions Pi and Qi is the sum, or the difference. Now, the signs would matter, but for the argument it's not so important, is sum or difference of the entropy of the observable and the cross entropy between the two probability distributions. We can also think this means that when we train a classifier, we train to minimize the Callback-Libeller divergence between these two distributions, because when applying the gradient, the entropy of the probability of the data actually vanishes. So we can very easily relate the Callback-Libeller divergence also to the core of training the classifiers. So this is really one of these measures of differences of probability distributions that crop up again and again when reading papers that introduce machine learning algorithms. It's important to know them. There's a second one called Jensen-Shannon divergence, which is a symmetrized version, because if you look at the DKL of P and Q, it matters in which order we pass the arguments P and Q, because the symmetry is broken because one is above the numerator and the other one is below, and we have this one here in front. So these are obviously not symmetric under exchange. There is a symmetrized version, but we use that less often. Okay, so why did we introduce this Callback-Libeller divergence? If we now take a look at the original paper introducing generative adversarial networks, this is just the loss function that we had introduced before. So the expectation value over the data of the logarithm of the discriminator plus the expectation value of the random number distribution, logarithm of 1 minus the discriminator applied to the generator applied to the random numbers. Without proof, the global minimum of this training is exactly the case where this minimizes the Callback-Libeller divergence. So in a very abstract sense, you can think of this generative adversarial network training setup as a way to write down two functions that when minimized, minimize the specific measure of probability between these two probability distributions. And I know this sounds very abstract, but you think of the one probability distribution as being the distribution over the space of generated images, and the other probability distribution as being the distribution over the space of your training data. And being able to successfully generate images means nothing else that you bring these two probability distributions as close together as possible. So this is now a slightly more abstract way of viewing it. But why is it important? Because now that we've realized that the generative adversarial network does nothing else than minimize some measure of distance between probability distributions, we can ask the questions, are there other measures of differences between probability distributions that we can use instead as the optimization target of a generative network? And there's a whole family of these. I'm just name dropping one of them because it's very popular in physics. Jesse talked about it in his seminar yesterday. And this is the so-called Wasserstein distance or earth movers distance. So very physically, you can imagine two histograms, two probability distributions as piles of dirt. And the Wasserstein distance is the amount of work, meaning how much distance do I need to move some volume of probability, and how much do I move this specific amount of probability to make two probability distributions equal. So it's essentially saying if I have these two sets of histograms that I want to get to improve, how do I move data between the different bins until the top and the bottom histogram improve. So you see the top histogram is some distribution. The bottom histogram is another distribution. And then we step by step move stuff around in the top histogram until in the end it looks like the bottom histogram. And the Wasserstein price we pay is, for example, we move these two bins from the these two volumes of statistical coverage. We move them from the first bin to the second bin. So we pay a price of 2 times 1 because we move two boxes one step to the right. So the Wasserstein distance is doing this operation until these agree. And specifically, the Wasserstein distance is the minimum, the infinite, over all possible transport paths. So you try all possible ways to map these two probability volumes into each other, and you define the Wasserstein distance as the cheapest way of doing this, as the cheapest way of making these two probability distributions agree. Okay, this is one of the moments where you're very unhappy because you've now found a very beautiful definition that does not seem operationable at all. How can you cover the space of all possible movement paths between probability distributions? Well, the nice thing is that there is a mathematical proof, again, not going into that, called the Kantorevich-Rubenstein duality. So some mathematics, as I said, don't get scared by that. But it very simply says that this Wasserstein condition can be solved by just minimizing the expectation value between arbitrary differentiable function applied to examples from the one probability distribution minus the expectation value of a function applied to another probability distribution. This function is a neural network with trainable parameters, and one just needs one additional condition to make sure that these are smooth. So essentially that the gradient stays below some threshold. But the key part is really this here. So essentially, without, as I said, going into the details of the proof, one can show that there's an equivalent formulation of this moving thing that is, again, very easy to express via neural networks, because now we've phrased this problem again as something that can be written as the loss function and that can be optimized for directly. Not going into details of the Wasserstein applications, but I think the most important thing to keep in mind here is that whenever there is a specific training problem you have in mind, thinking about the probability distribution, what you're doing to the probabilities and what you're trying to solve is a very good way of addressing the problem of a limited amount of performance. So I'm looking at the clock and I see we have 10 minutes left. Okay, let me do something a bit unconventional because I want
Gregor,
to... Yes?
sorry to interrupt you.
Sure.
It's been already 75 minutes or so.
Oh,
If it is okay, do you think this is a good time to stop?
it's also okay. I thought they started at 45. I'm very sorry. Oh, yeah.
No, yeah, so 9:45.
I was going for 90 minutes because I didn't calculate right in my head.
Okay.
Okay, very good. Now this is a very good time to stop.
So this one works out for your lecture schedule?
No, this works perfectly.
Okay, so great. Thank you very much, Gregor.
Thank you.
So we apologize for the inconvenience and then sudden change in the schedule. I think we got Professor Tegmark ready, so we will have his colloquium talk at 11:20. So I'm sorry we have only 15 minutes break, so we will resume in 15 minutes.